Hi, everyone. Welcome to the ATIC seminar. Today, we have Peter Case from the University of Warwick. He's advised by Sayan Bhattacharya. Peter has several cool works on maximum matching in several online and sublinear settings. So today, he'll talk about his recent work that appeared in Fox 2023. Over to Peter. Thanks, Peter.
So the paper title is Dynamic 1 plus epsilon approximate matching size in truly sublinear update time, but it's a bit deceiving. This is really a sublinear algorithm. So 1 plus epsilon approximate sublinear matching should be the title, which just felt like the dynamic thing is selling it better. And I co-authored this paper with my supervisor, Sayan, and Bhattacharya from the University of Michigan. And at the time of writing this, I was interning at the Max Planck Institute for Informatics in Saarbrücken. So what is the setting we are considering? Is the approximate maximum matching problem, where our goal is to find a large matching of G. Mu of G will always stand for the maximum matching size. And we will say that something is alpha approximate if mu of G is less or equal than m times alpha. So alpha is greater or equal than 1. So just an illustration, this is a 3/2 approximate matching there. So I will refer to, I'm not sure if it's standard in researcher, but I will refer to the problem as the search version, where we actually want to find the matching itself. But in the sublinear regime, we have to think about the value version, where we only get a matching size approximate. That is, we only return a round number, which is approximately correct. So just a few simplifying assumptions throughout the presentation. Think of the graph as it is very dense. In most of these models, there are technical tools which allow you to make this assumption, or it doesn't even make sense to not make this assumption. And also assume that there's a large matching in a graph. The same goes for this assumption that it doesn't make a big difference if you don't assume it for technical reasons. We will consider two settings, and I will show a very simple connection between these two settings. So the first one is the sublinear one. Our goal is to estimate the maximum matching size of the graph. And the big challenge is to do this without accessing the majority of the graph. So we want to be polynomially sublinear with respect to the number of edges in a graph. So let's just say with respect to n squared for dense graphs. Matching size approximate being approximate being alpha approximate is defined the same way as in the search problem. Oh, sorry, I think I keep the slide there. Or I did not. Right. So we are being sublinear in time, which does mean it's a question, how do we access the graph? We don't really have time to reorganize the data in a convenient format. So the two kind of models people usually consider are the adjacency matrix query model, where we can ask for specific two endpoints, two nodes, whether they're connected within the graph, and the list queries, where we can ask for vertices ith neighbor. In this paper, we considered exclusively adjacency matrix queries because the dynamic implementation does not require list queries. But I strongly believe that this paper can be generalized to list queries, but don't quote me on that. The second problem we are going to consider is the dynamic matching problem for the value version, fully dynamic in particular. So here we are given a graph which is undergoing edge insertions and deletions, something like that. And our goal is to maintain an alpha approximation to the maximum matching size at all times. So something like this. So we are really maintaining just a single number. Our objective is to minimize the update time. And in this paper, we will always think of update time as the average update time over some series of updates, amortized update time. But do note that every result in this paper can be generalized to be worst case, but it's easier to think about it to be amortized. So why these two settings in particular? Well, there's a very simple connection between these two settings in one direction. So I claim if you give me an alpha approximate sublinear algorithm, which runs in time n to the 1 plus delta, then there's a very simple reduction which just says that there's a marginally worse dynamic algorithm with update time n to the delta. So we save n and it turns into update time. So why is this? Well, it's just periodic recomputation. So we can describe a simple dynamic size algorithm based on any sublinear algorithm by just periodically recomputing the matching size within the graph and weighting. So in step one, we compute an alpha approximation using a sublinear algorithm. It will take us into the 1 plus delta time. We wait for about n updates, assuming the matching size is large, and in the dynamic setting, technical tools allows us to do this. This approximation will stay correct. And then we just recompute. And we can amortize the n to the 1 plus delta sublinear computation over these n updates to get the update time of n to the delta. So this is a very straightforward connection, but prior to our result, as far as we are aware, this connection did not lead to new dynamic size algorithms because the sublinear regime was sort of behind the dynamic regime in terms of results. So what are the existing results? Well, for dynamic matching, it can be said that it's extensively studied. These are, I think all of the papers up to the publication point, and there were papers since. So it has there are a complicated landscape of results to talk about here. And this is for the search version where we actually maintained a graph. A long line of papers were considering polylogarithmic update time, which is essentially optimal. Obviously, can't hope for much more for that. That's the holy grail in dynamic algorithms. And the approximation ratio got down to 2 plus epsilon, depending on randomization and determinism. There's an interesting step at 3 alpha approximation where root n update time is possible. And around 1 plus epsilon approximation, you can get O tilde n update time. But this can actually be achieved just by simple periodic recomputation every epsilon n updates or so. So those results, I'm not saying those results are simple. These do gain some small advantages over n, but that's where you would expect to be just by recomputation. And then there are some other trade-offs between 3.5 and 2. The only hardness result here used to be, at the time of the writing this paper, was a result which showed that you need polynomial time for sure if you want to maintain an exact matching. And I think even if it's just a size estimate, but I'm not 100% sure even for bipartite graphs, and even if just there are edge insertions. Now, very recently, there was a paper by Liu which showed that under the approximate dynamic OMB conjecture, which I'm not going to get into, it's a relaxation of dynamic OMB, 1 plus epsilon should be hard. So this is what you should expect as these algorithms are getting. For the value version, there are actually some better results. You can actually cross to approximation, which was shown at last SODA. That crossing to approximation actually uses sublinear algorithms as well, just not in a black box way. And you can also beat 3.5 by a tiny bit, by some absolute constant. So for the value version, the landscape is a bit different. And in terms of hardness bands, is different as well. I'll show those at the sublinear, sorry. Hardness bands for the value version, they don't actually exist, only for just exact. I quoted that wrong. So let's just go to sublinear algorithms. I hope I didn't lose you there. Sublinear algorithms have somewhat less research into them, and they are more recent. I'm not including everything here, of course. There's a very nice paper which appeared at Fox 21, which gave 2 approximation about O tilde n time, and you cannot hope for anything better than O tilde n. It's easy to see that that's the minimum you can dream for. Quickly afterwards, some authors shows that you can suppress to by a bit if you go above n by a bit. And then at stock club, sorry?
I have a question. So here, again, it's sublinear algorithm for computing just the value, or?
Yes, just the volume. Right, this is just the value. So in a sublinear regime, you cannot compute the matching itself. You can always only hope for the value. This is relatively easy to see. Think of a graph and you have adjacency matrix squaring access to it, and say every edge exists with some constant probability, like, I don't know, d over n or something. And in order to find a single edge, that should take roughly n time because they're just so sparse and they're completely independent. So to find a constant approximate matching, you would need to spend that square time. So in a sublinear regime, there's nothing, you cannot hope for a constant approximation unless you make some strong assumptions, which is actually a search version. So in a sublinear regime, it's always value version. Good point. So in stock last year, there were 2 papers, one by our group, which showed that you can get 3.5 approximation in slightly less than n squared time. So like n to the 2 minus epsilon squared. That's how you should imagine it. And the other authors actually showed that you can beat 3/2 slightly again. But the point is that in both settings, there's nothing positive for 1 plus epsilon approximation regime apart from results which don't sway polynomially away from the trivial. So it's kind of an intriguing question whether you can get to 1 plus epsilon. Note that since the writing of this paper, hardness results have appeared, which I added to the presentation today, namely that in a sublinear regime, you cannot beat 3/2 in less than or tilde n to the 1.2 queries. And also that you cannot beat n squared by a polynomial gap. Only for 1 plus epsilon regime, only if that polynomial gap depends on epsilon. Now the dependency is complicated. Right. So what is our result? The core result is a sublinear algorithm, which gives a 1 plus epsilon approximation to the maximum matching size, assuming that the maximum matching size is large. We give an additive approximation, that's why. And it has update time U tilde n to the 2 minus a function of epsilon. And think of something very, very tiny. Something like 2 to the minus epsilon to the 1 over epsilon. It is a very, very tiny improvement, but it's a polynomial one for every value of epsilon. So we do give an additive approximation in this model, but also note that in the adjacency matrix query model this paper is working in, the additive approximation is provably necessary, which means that this is the best you can get. Right. So what does this mean? This means that there should be a point moving there. We put the first 1 plus epsilon approximate result over there. And as I said, a paper since the publication of this one at STOCK this year has shown, which that will not be, well, it's been published, so it's online. It has shown that indeed you need at least n to the 2 minus a function of epsilon time. Now, there are gaps between these two functions. But up until what dependency is on epsilon, this problem is mostly resolved. I think they also say this for the adjacency matrix queries. So for this queries, I'm not sure, but more or less resolved. So it's quite interesting that it happens so quickly. So recall our reduction. We said that if we have an alpha approximate sublinear algorithm in n to the 1 plus delta time, then we get an alpha plus epsilon approximate dynamic algorithm with update time n to the delta. So this almost instantly gives us our second result, which is a 1 plus epsilon approximate dynamic algorithm for the maintaining the size of the matching, which runs in with update time n to the 1 minus a function of epsilon. So truly sublinear for any epsilon. The algorithm works against adaptive adversaries, has worst case update time, but these technical terms are kind of secondary properties here. And do note that in the dynamic regime, you can get rid of the additive approximation through vertex classification techniques. So this is actually a purely multiplicative approximation. And also the algorithm can be made to be a function of root of m instead of n. And as I mentioned, just rebuilding after every epsilon mu of g updates, you get roughly n-time algorithm. So this is the first algorithm which truly beats, which polynomially beats the trivial approach. So on this picture, it will go to the same place, really. Right. So let's talk about how do we approximate the maximum matching size in a sublinear model. And let's just first consider a naive idea, which was considered actually by quite a lot of people in literature longer ago. It's simply by sampling. That would be the first thing which comes to mind. But the issue is that dense regions will very much dominate the sample. So if a graph which looks something like this, a big clique and then a sparse part, then if you sample, you will rarely hit the place where the matching is coming from. It's not going to be very representative. You need to do something smarter. In fact, it's not easy to show, but it has been showed that you need, you cannot get polynomially less samples than the number of edges to get an approximation this way. So what is the general approach? And this is not specific actually to matching algorithms. So this is used for other ones as well. for other problems as well, is that we choose some static algorithm, A, which has some nice properties, small parallel depth, highly randomized. Its computations are very local. I mean, it would be quite hard to grasp which properties this should be, but this is what you should think of. And we sample some small number of vertices, say some polylog vertices, and we check whether they are matched under this matching or not, the matching computed by this algorithm on this particular graph. And then we just extrapolate the ratio of these matched vertices towards the whole graph. And we will say that that's a good approximation. As far as I'm aware, and I might be wrong here, all of the sublinear matching algorithms actually do this. So what does this mean? This really means that we are looking for an algorithm whose output which we can locally query without reading the majority of the graph. So the real problem here is about matching oracles. It's really about whether I can construct some oracle which tells the match status of a vertex, and we usually also ask for the edge matching it if it is matched, under some matching. And of course, this matching has to be consistent throughout the graph, otherwise our extrapolation wouldn't make sense, right? So somehow consistently for the whole graph, it needs to be able to tell this very, very efficiently. Right, to give an idea of why is this possible, let's look at the beautiful result of Sohail Besnash, well, I don't want to butcher his name, from Fox 21, where he showed that you can do this process of locally querying a vertices match status efficiently for random order greedy matching, which is known to be, it's a folklore fact that it's too approximate. So random order greedy matching can be just thought of as you assign values between 0 and 1 randomly to the vertices, you go through an increasing order, and you greedily build the matching as much as you can. So something like this. We are moving upwards. And say we want to query a specific vertex, a specific edge, the one in the middle, we can instantly actually exclude a lot of directions we don't want to go in, because the randomness is guiding us towards how this process evolved over time.
Sorry,
so we can,
I have a
yes?
question, sorry. So what exactly are we doing greedily? Are you just picking edges?
So the static algorithm, so I'm giving this just as an intuitive example of how can this be achieved. So we will be doing something very different in a second. So the static algorithm here is random order greedy, which assigns the values to these edges between 0 and 1 uniformly at random. And this defines the random order over the edges. And we build the matching according to this. And the reason why I kind of wanted to show this example is on this algorithm, it's quite clear to see that as I'm trying to locally query this very specific static structure, I don't have to explore the majority of the graph. The majority of these computational directions will be non-important from the perspective of my query. And in fact, I can very efficiently arrive at the conclusion that the middle where the edge had to be edged without reading the majority of the edges. And this is kind of the thing we want to look for, an algorithm which has this property, this local computational property. Yes?
Edge, so let's say you're looking at this edge of weight 0.4. So to figure out whether or not it belongs to the matching, do you have to query all the edges of weight less than that? Or
so in order to tell for this edge in particular, for this algorithm, you actually have to query every edge in the neighborhood, right? Because either of them could have came sooner. But to continue your queries, you don't need to look the ones which came after, because those did not affect the matching status of this particular edge. So you will need to query a lot of edges. You will end up querying over tilde n under this algorithm. It's far from trivial to prove that. But the point is that majority of the computational paths you would need to export to calculate the complete static solution is not important from the oracle's perspective. So this is kind of what we are hoping for.
Okay, thanks.
So as I said, the problem is about matching oracles. So getting these oracles which efficiently tell match status of a vertex under some fixed matching. Right. So we have to choose a suitable static algorithm and try to implement it in the sublinear model using some oracle-based technique. Our choice for a sublinear algorithm is a well-known semi-streaming algorithm by McGregor, which is like a low-space algorithm which only accesses the edges of the graph a few times. But we don't really exploit neither of these properties. since we wrote this paper, we realized that there are many more candidates which can be implemented this way. Right. So this algorithm has quite a lot of these standard classic matching literature, like Hopcroft and all of this. Algorithms work by augmenting path elimination. So what is an augmenting path? Let's fix M to be an arbitrary matching, which our algorithm has computed up until time point t or something, and let M star be a maximum matching. And the union of these two matchings were defined in following structures. It will be of Mach degree 2, of course. There will be points where they match. They will form cycles. They will form even length bands. And on these structures, they have the same edges. They are not much different, but they will form odd length paths where the maximum matching is one longer. And that's an augmenting path, which can be used to augment M. So each of these paths can be used to extend M by one edge, which means that if all of them are very, very long, then the purple matching has to be roughly the same size as the red matching. So this is very standard matching stuff. This is what quite a lot of these classic algorithms exploit. So if all of them are of length 2k plus 1, then the matching is at least k plus 1 over k approximate. This is a folklore fact from literature. So what idea does this give? A simple idea is to repeatedly try to find an absolute constant fraction, some small constant fraction of fixed length augmenting paths, and repeat this process until very, very few short augmenting paths remain. And at that point, we can say that the approximation of the algorithm is quite good. So this is what McGregor's algorithm does. It requires a constant number of iterations. Yes, and it requires a constant number of iterations. So how should we imagine such a step where we look for a constant fraction of augmenting paths? So I will call such a step as an augmentation phase, where we find a constant fraction of some fixed length augmenting paths, and we use them to extend the matching. So now we are describing static processing. So let's say that we started with M, which was a purple matching up until time point t. This is what the algorithm calculated. Think of it as a greedy matching initially. And we fix some constant, which is roughly 1 over epsilon, or it might be smaller, depending on where the algorithm is running. And we are looking for augmenting paths of that length with respect to M. And this will, if we find a constant fraction of them, we can actually improve on the size of M dash. Actually, there should be alpha minus epsilon, sorry, not alpha plus epsilon. McGregor's does this with some exponential number of phases, but it's constant. That's the point. It's not efficient, but it's constant. There are actually ones which do this in polynomial for bipartite graphs. So how does executing this thing look for, say, 5 augmenting paths? We will first brute force random put vertices into 6 categories as 6 layers. And some small constant fraction of the augmenting paths will behave in such a way that they start from the first layer we chose completely random, and they go till the last layer. This will happen to an exponentially small fraction of them, but it will happen to a constant fraction of them with high probability. Right. So we will really just focus on this small constant fraction of augmenting paths, which happen to survive this brute force randomization we did at the beginning. And we will try to find a constant fraction of these augmenting paths. So how do we go about this?
What are the black edges here? The red edges?
So the black edges are just edges in the graph. The red edges are edges in the maximum matching, which we don't know what it is, but it has to be one something. And purple edges are the ones we have already found.
Okay.
So vertices in layer 1 have to be free nodes if a augmenting path survive this randomization process. So what we will do is we will just first calculate a constant approximate matching between the first layer and the second layer. That's all what we do. So that's going to be the green matching here. And we say that if this matching has some reasonable size, so say number of vertices times some small constant we will fix, but an absolute constant, then this was a successful step, and we proceed onwards. And we proceed onwards quite logically. We look for the third layer endpoints of these alto nodes we matched. What we did is we essentially started to compute prefixes to the augmenting paths. That's what we are doing here. Now we repeat the same process, but now we are connecting layer 3 with layer 4. We compute a constant approximate matching, but as can be seen on this picture, this can go wrong. But at this time, we don't really know this. We concluded that we matched a lot of vertices, so far we are good. and we proceed to layer 5 and hope to finish these prefixes. But once we get to layer 5 and we want to compute matching between the endpoints of those prefix paths we have found and layer 6, we will observe that we can't do enough of them. Like, it's going to be smaller than this constant fraction. We will say no problem. We will ban the endpoints where we got stuck at in the previous layer. Like, these were not good directions to go towards. We can't finish the augmenting paths in this direction, and we just backtrack. Why can we do this? We will set this delta to be so small that it's kind of ensured that the vast majority of the vertices we ban in this step are indeed bad. We will barely lose out on some augmenting paths. A very even tinier fraction of augmenting paths will be banned due to this process. And we repeat this until we actually get to the end. Like in this picture, we get lucky and we are just done. So do note that in each step, if we either moving to the right or we are banning vertices. And because we expect these matchings to be always like constant times n large in every step, even if we ban, we are banning a constant fraction of the vertices. So this process will actually have a very high constant, but a constant number of matchings involved. That's the point. Right. So in order to find k augmenting paths, we will set delta to be something like k to the minus k, and we will find roughly the same fraction of augmenting paths if you work out the math. It's rather messy, but the intuition, I think, is relatively clear. So the big thing to remember is constant number of phases. And in each phase, what we do is we calculate a constant approximate matching in a specific vertex-induced subset of the graph. That's the key thing here. It's a very simple thing we do in a particular step. Right. So the challenge is, how do we implement this in a sublinear setting? So it's not instantly clear that this is actually a somewhat local algorithm. Why does this not explore the whole graph? And here we will introduce a idea from Stock 23 paper, sublinear paper, which we called, and I'm not sure what they called, the hidden matching problem. And I will show why this is relevant. So hidden matching problem is the following. There's some, say, bipartite graph, it might even be bipartite, but not necessary, which has some hidden subset of the vertices A. Something like this. I know that inside of A, there's a relatively large matching, say n times epsilon, but I don't know the vertices of A. What I do know is that I'm given an oracle which can tell for one specific vertex of A, one specific vertex of the graph, sorry, whether it is part of A or not. And it runs in slightly superlinear time than n. So what does this say? I can't query all the vertices. That would take me more than n squared time. But I can query a very high polynomial of the vertices. I can query n to the 0.99 fraction, not fraction, n to the 0.99 vertices, but not all of them. And what is my goal? My goal is to construct a matching oracle for a constant approximate matching inside of A. So without having very explicit access to the vertices of A, I want to construct a very efficient oracle to matching inside of A. So I think the more you think about this problem, the more it seems impossible. And before writing this paper, there was a while that we wanted to prove exactly that this can't be done, or almost exactly, but surprisingly, this is possible. And my goal is that this oracle I get out of this process should run in roughly the same time. Maybe it gets like an n to the epsilon blow up, but it should still be almost n. So I should barely get any blow up. And I want to do this construction in less than n squared time. Right. Why is this, like, this might have seemed very arbitrary. Why did I come up with this? I will now show why is this. I claim that if you have this, you have implemented McGregor's in the sublinear setting, the algorithm I described previously. So let's assume that we are trying to implement McGregor's and we want to do this one of these augmenting phases, and say we started from a greedy matching, which was 2 approximate. Say we are looking for 3 augmenting paths of 5, whatever we chose. We have an oracle under this previous matching we have calculated. If it's a greedy matching, we can pick one from literature, which runs in roughly n time, which was kind of the requirement of this hidden matching lemma. And also a slight comment that the randomizations of the layers is just O n time because we just pick a random value for every vertex. So what do we actually need to do in order to get a matching oracle for this augmenting phase? Well, in each step, we will pick from a subset of the vertices in whatever layers or whatever, which have been either matched or not matched previous, there's something like that. And we need to find a constant approximate matching between the current layer and the next layer. So what this means in the oracle world is that we need to find an efficient oracle for this constant approximate matching. So this is what this means in the sublinear regime. And now let's think about what the hidden matching lemma does to us. What is going to be our hidden set here? Our hidden set is going to be L1 union L2. How much time does it take us to query whether a vertex is in L1 or L2? Well, the randomization is constant. That's what we did statically. And then we just need to be able to tell whether it is matched by the underlying matching or not, for which we assumed we have an oracle which runs in roughly n time. So we can essentially tell membership in this hidden set in roughly n time, as we expected. And if we have this hidden matching oracle, we can solve this hidden matching lemma, then we can give an oracle to this green matching, which also runs in roughly n time. And we proceed, and we recurse. And this is what we do. So this might have been very hand-wavy, but I hope it's convincing that this hidden matching lemma is actually incredibly powerful. Right, and when we can just proceed onwards. And we will need to use more and more of these oracles we have calculated, but everything here is constant number of layers, constant recursion, so every blow-off will be fine. So let's talk about this hidden matching problem, because I hope I convince you that this is almost magical, but it can be done. And do note that this is, we're building on another group's work here when we're discussing this, so we don't claim novelty to this completely. So what was the hidden matching problem? We have a bipartite graph, a hidden set we can't quite access. We can't access all of it, just like m to the 0.99 of it. And we want to get a good, like a constant approximation, sorry, an oracle to constant approximate matching inside of this oracle. So how will this work? Let's fix k to be n to the 2 epsilon. And let's sample k sets.
Quick question,
Sorry.
I just want something to be clarified. So in that augmenting path algorithm, I thought we actually need to find the augmenting path. So here, when you said in this hidden matching problem, we need to compute the matching itself and not just the size, right? Or is it?
So, right. Sorry, that was confusing. So everything here is about oracles in the sublinear regime. So at the end of it, so once we have computed this hierarchy of oracles, which can tell the match status under the matching we want to compute at the end, which is 1 plus epsilon approximate, we will query log n vertices and we extrapolate to the graph. But until that point, we will just recursively compute stronger and stronger oracles.
I see.
So I think in every step we are taking oracles to construct a stronger oracle. So we are actually not exploring much of the graph. There will be steps where we actually maintain quite a bit of edges, but still sublinear number of them. But we are not expecting to explicitly find a large matching at any time point. What we are expecting is to get ever improving hierarchy of oracles.
I see. Okay, thanks.
So let's fix k to be some constant n to the 2 epsilon, and sample k sets of edges from the graph uniformly at random. Like you just pick random pairs of vertices and you check whether there's an edge or not, in n to the 2 minus 3 epsilon time. So these choices might seem a bit odd and they're not very important. The thing to note is that their product is the total number of edges we sample is n to the 2 minus epsilon. So this takes us sublinear times 2. So it will look something like this. We sample these. These are the EIs, these different colored sets. And then at this point, we calculate greedy matchings inside of these EIs. So we just calculate maximal matchings inside of them. That will look something like this. So this is our setup. This is something we will do statically. We did not explore the majority of the graph, but we have found some useful edges. That's what we hope for. There will be 3 cases we need to consider. So first, there's a very simple case, which would be the most appealing thing if we could guarantee, but we can not guarantee at all times, is that one of these matchings is actually quite good, we calculated. That is, it's already constant approximate inside of the secret set. Now, this we can test by just sampling its endpoints and sampling randomly from its endpoints and testing whether they are in the secret set or not. And if this is indeed the case, then we have a very simple oracle. Our oracle just really need to check whether a point is an endpoint inside of this good matching we have luckily found, and to check whether it's part of A. So this is the easiest thing which can happen and instantly gives us an oracle. Right. But unfortunately, this is something you can't expect to happen. So then I will describe the second case, which I will call the tricky case. I mean, I could have come up with a better name here. Now, let's fix a maximum matching, which we obviously don't know, inside of A, the black one. Sorry, I think I should have called it M star A, not MA star, but never mind. So that's the maximum matching inside of A. We only know that this has some reasonable size, like this is not tiny. It's like epsilon n. And I will say that I will consider the following case. One of these matchings we calculated ignores both endpoints of some constant fraction of this black matching. Okay, this might have been a complicated statement to swallow. Point is that it looks something like this, that there are some fractions of these black edgings, which is like a large matching inside of A, such that this matching we calculated, one of the K matchings we had, ignores both of their endpoints. So why is this good for us? Well, let's look at the graph, the induced subset of this graph, which ignores the endpoints of the red matching we calculated. I claim that this induced graph has small maximum degree, like n to the 3 epsilon or something tiny. Why is that? Intuitively, this red matching is a greedy matching. And the induced subgraph of its complement, if it would be dense, we would have hit it with a random sampling process. That's the simple intuition. So this red matching is just a greedy matching of the graph. Its complement must be sparse, otherwise we would have hit it during the sampling. So its complement is going to be very, very sparse. But we also know that that was our assumption in the tricky case, that it ignores a lot of these important black edges. And fortunately enough for us, for this instance, there are already algorithms in literature. That is, for small max degree graphs, you can actually get constant approximations very, very efficiently. So all we need to do is use one of these oracles in literature to query the complement of one of these MIs. So these are two cases. But we clearly haven't considered all cases. So what did we not consider? Well, we're not in the easy case. So none of these matchings we calculated hit a lot of edges inside of A. None of them are instantly lucky. But we are also not in the tricky case. That is, most of these matchings don't ignore both endpoints of this black matching we're looking for. So they look kind of like this, that they expand outwards from A. They have a lot of endpoints inside of A, a lot of endpoints outside of A. Now this gives the following intuition. We just do a recursion. We sample some vertices of A uniformly at random. We do this by just picking a vertex, checking whether it's A, and repeat. So those red vertices. And we know that the union of these matchings is expanding very heavily outside of A. That's what these two that we are in complement of these two cases guarantees. Which means that if we just look at the neighbors of these red vertices inside of the matchings we calculated, most of them are going to be outside of A, and we will just band them. This case allows us to actually efficiently query the outside of A. Even though we can inefficiently query membership on A, if we are guaranteed that we are in this case, we can efficiently query the outside of A, which is as good, of course, as querying the inside of A. And we can guarantee, and this is somewhat technical, but the intuition is what I described here, that this is going to be an edge set expanding outside of A, that we will hit the constant fraction of the vertices. And we just recurse until the vertices outside of A are just going to be very, very, very rare. So we will end up either in case 1 or case 2 whatever happens, right? So this is a fairly technical tool, but I hope I gave some intuition how this magic is done. Right. So let's just rehash how this hidden matching oracle is used in order to implement McGregor's in the sublinear setting. We need to do this augmenting phase. We can query whether a vertex is matched by the purple matching efficiently. We can query the randomization because that's done in one time statically, that's fine. So our hidden set is first just going to be the free vertices in L1 and the matched vertices in L2. So the endpoints of the purple edges in L2. We apply the hidden matching oracle and get a constant approximate matching oracle to the green matching. And in order to tell which vertex is in the yellow matching, we just need to check whether there's an augmenting path up to it. So we need to check whether it is matched by the purple matching and whether its endpoint in L2 is matched by the green matching. And everything here is just references to previous matching oracles we calculated, a constant number of them, importantly, and all of these run in roughly n time. So every future oracle we compute will also run in roughly n time, and this will amazingly suit the hidden matching lemma, which we will just call repeatedly again and again. And there's a constant number of iterations, so these oracles will never blow up to be running in more than n to the 1 plus O epsilon time. And when we compute any of these oracles, the most expensive step is really the sampling, which is still slightly sublinear in the total number of samples. So even though the oracles run very efficiently, we do some less efficient computation to get them, but it's still sublinear, so we're fine. Okay, right. And as I mentioned earlier, we do this until we are confident that enough augmenting paths have been eliminated such that the matching is 1 plus epsilon approximate, at which point we sample some polylog vertices, we check like half of them are matched or something, and we extrapolate to the whole graph, that this is roughly representative of the whole graph. So that's the end step in every sublinear matching algorithm. Right. So what takeaways I would like you to have from this presentation? Well, obviously, the main result is that we can get arbitrarily close to the maximum matching size in sublinear time, even for general graphs, actually. McGregor's doesn't require the graph to be bipartite, note here. And this already, since the writing of this paper, this had found applications outside of matching. I've checked the citations, and there was already a TSP paper which uses this to get a trade-off, and an Earth movers distance paper, but don't quote me on what that means, because I'm not sure. But of course, this has instantly found applications in dynamic matching itself. But just to say that this is kind of an interesting observation in general. And the other thing is that prior to this, we did not, I'm unaware that the sublinear algorithm sort of beat the progress on the dynamic matching algorithms. And in particular, in case of dynamic matching, it might just not just beat it, but it's like provably beat it if you believe in the approximate dynamic OMB conjecture. So this is an avenue to explore potentially for other sublinear / dynamic problems. But this is anyways. And thank you for listening. I hope I didn't rush it. I have the habit of rushing online things.
That was a great talk. Thank you so much.
Oh, I did rush it, sorry.